All right, so I'm going to show you 105 and 108. This is going to show you the MNIST data set and then an attack against it. So first, we're just going to classify these images. Now, what these are, the MNIST data set is a set of digits written by people taking the American census. So it's just a bunch of handwritten images. So you can import them and then print them out. And here's what they look like, 5041 and so on. And the point is, most of them are pretty clear, but some of them are sort of messed up and hard to tell. And so we're going to train a machine learning system to figure out which of those categories they're in. So the test, I think it has 70, the training set contains 60,000 images, and the test set, this should say test, contains 10,000. So we're going to train it on 60,000, and then we're going to test it on 10,000 images it's never seen before to see if it worked. And so we're going to make first we're going to make a binary classifier. So all it's going to do is evaluate them as a 5 or not a 5. So we're going to label all the images. We got labels. The ones that are 5 is going to be true, and the others are going to be false. And so now your training set contains 5,000 true and 50,000 false, and your test set contains 900 true and 9,100 false, because of course there are 9 times as many that are not 5 as 5. So here's the model. We have the input image. It's going to go in a bunch of pixels. Then it's going to have adjustable weights. The pixels come here. It's just going to feed them all into one neuron. And that neuron is just going to have a slope and intercept for the input data from each image. And it's going to have a value. And that value is going to be, if it's high, it's in one category. If it's low, it's in the other category. The simplest kind of thing, a binary classifier. And so you can create the thing and then just fit it. It will train it. And you see now it shows how many epochs of training to do. Before we just chose a number. What it can also do is it can take these small steps. And what it does is it goes until it's getting worse. It's going to slide down the edge. When it hits the bottom, it'll make one step that makes it worse. Then it knows it's at the bottom and it quits. And you can see that. It was 78.6, and anyway, it's not that easy to see here, but anyway, that's the idea. So then you can measure accuracy with various techniques. And this is one way to do it, to measure the accuracy of your model, is to split the training data into 3 subsets and train it 3 times. Train it on the first 2 and test it on the third, train it on the first and third and test it on the second, and so on. And you get a statistical measurement. And if you do that here, you get measures of 95%, 96%, and 96%. Now, that might sound pretty good, but remember, 90% of the data was not 5. So if you just labeled them all not 5, you'd get 90% accuracy. So it's not as great as you might imagine. And another way to measure the quality of it is with a confusion matrix. Here's the 4 categories. This is not labeled not 5 and correct not 5. This is how many were wrong. This is labeled 5 and correct. This is how many were wrong. So you can see the model incorrectly called 1,891 of the 5s not 5. So you could argue it did pretty bad there. There's other measures. There's something called precision, recall, and F1 that are just statistical ways to put a number on your model and see how good it is. Anyway, so that's what this one is. This is designing a classifier. And then we're going to do an evasion attack in 108, which is what I wanted to show you. And hearing some funny, let me try muting this. That might get rid of that. All right, so now for an evasion attack, you can train these models. If you know the model, you can carefully design attacks that will confuse the model. And this is what I thought was very important. So here we have a model, and we're going to train it on 100 and have a test sample of 500. It doesn't matter, but we're going to view some samples. So here they are. The only thing we're going to use is 5s and 9s, and we're just going to tell the 5s from the 9s. So you see, here's a 5 and a 9. What's up here is the label. So those are pretty easy. You train a classifier, and then there is a Python library that includes these attacks that people have developed. So it can very carefully plot what changes to make in the pixels to confuse the model the most by looking at the weights and figuring out which weights have a large effect on the output. And if you do that, it can modify the images. And what's very interesting is the modification. So here's the original image. Let me just zoom in on this to make it easier. Okay. So here's the original image. This is a 9, and the model detected it as a 9. But when you add this snow to the outside, now the model thinks it's a 5. And here's a 5. But when you add a little snow over here, the model thinks it's a 9, and so on. And this is what I was saying earlier. This wouldn't fool a human. The human would just ignore this noise out there. The model did not learn to do this the way a human did, by looking up here, finding the curve, finding a loop, and deciding that must be a 9 because there's a loop up here and a stick down there. It just did some unknown correlation of all these pixels in some pattern. And for some reason, the model decided that these pixels over here were real important. And if those pixels are bright, it must be a 5. So this is a fundamental problem with machine learning models. It learns something strange, and now it's going to get confused. Like this makes it think it's a 9. That would not, none of these would fool a human. And that's why, as I mentioned, in recent news, there's a recent new model where they take the camera image and they modify it. They analyze it a little bit before they feed it to machine learning by doing things like finding edges. And then they feed the edge values into the machine learning model, so it'll do something more like what a human does. And that makes it faster and more accurate and easier to train. Again, imitating our biology. So anyway, there's a couple more to try there if you want. You can see an attack and see how it works. So I'm going to stop this recording.